So the agenda is, first I will do a short introduction, then we look into how LLMs actually work, especially the attention mechanism. We go into scaling laws, and then we look into the different training types of LLMs. We look into the evaluation, and after that into parallelization techniques and also how we use LLM on our HPC systems. So first introduction, basically a little bit more than 2 years ago, ChatGPT was released, and it definitely changed the world as we knew it before. So for me, it took away a lot of boring type of work, right, which I didn't like to do, and much more productive at writing like Python scripts or data processing, whatever. I really like to use it there. And this is the current state-of-the-art leaderboard for both commercially available and some open source LLMs. We see OpenAI O1. It's a reasoning model, which is first close after as DeepSeek, the Chinese model, which was released some weeks ago. And yeah, you see Claude, which is also a commercial model, but also a lot of open source models like Grok and Llama 3, for example. And the reason open source model exists, that's the model we can use on our HPC systems, right? So the closed ones we don't have access to. So if we just look at the open source LLMs for this talk, there's also a separate leaderboard from Hugging Face, which you can look up. So the most popular open source LLMs are basically Llama 3 series, Mistral AI, especially for German. I like Mistral models. They're quite good at speaking German and European languages. And the new kid on the block, DeepSeek, which is yet hard to host, but has excellent results for those benchmarks. So let's hop right into how do these LLMs actually work. So basically they're next word predictors. And if we start with the sequence of words, so just for clarification, I use a sequence of words instead of tokens for making it easier to understand. So the actual LLMs will use tokens instead of words. But if we have a sequence of, let's say, HPC is all the transformer, the GPT model will predict probabilities of the next word, which is, in this case, I think, need, right? HPC is all we need. And this is basically the principle how it works. And if we look into the details, so again, those words represent tokens. They all have their correspondent embeddings. For example, HPC has the meaning encoded into an embedding that is static in this case. And then is has its own embedding, all has its own embedding, and we, and so on. And this is how it is in a static way. So the embeddings are just looked up and they contain the meaning of the single word, which is not too helpful yet. So the GPT model uses instead tokens, and that's to provide a balance between linguistic flexibility and also the computational efficiency. So they are split up words, and so they can make better and understand different languages better. But there's still problems with numbers and also code. And one point here is that tokenizers matter a lot, but for the latest models, the tokenizers became quite good. So even for, let's say, German language, which is globally a niche language, right? So let's go.
In context, the tokenizer is what splits the sentence into.
Yes, which splits the words into tokens. So let's go into a problem that we have. We use those static embeddings, right? So there are words that have different meaning in different contexts. For example, she decided to set the table for dinner because the guests arrived. But there's also this word in a context that says the sun began to set, right? So, and also he bought a set of tools to fix the broken chairs, right? There's many different meanings for the word set, although it's the same word. It didn't change, right? So if we look at embeddings that are just looked up, they would be all the same, not regarding any context. And this is hard to predict the next word after you have such a generic word as set, right? So what we need a mechanism that enables the sequence to influence each other's embeddings, basically. So and this is the attention mechanism. So if we use the attention mechanism, we see that each token that comes before a certain word here will influence its embedding. So the meaning of the word will be set in the right direction. So if we look at those embedding vectors as actual vectors, they get influenced by surrounding words through this attention mechanism. So we see set is so just a single word set has an embedding which has a direction, and after it is in company of decided to set the table, it will get moved to a meaning that's more close to this context, or a set of tools, whatever is another meaning, right? So what I want to say is when you imagine an input text that is an entire crime story, right? Like a book. And the crime story goes all the way up to the end. And the last sentence would be the reason of his death was. So the final word in this sequence is just was, okay? So the embedding vector of was has to be influenced by all the other words that came before until you're finally at this point was. And it gets updated by all those words before, and that's the reason why the model can accurately predict the next word, and because it has all those inputs before. So if you look at it more closer, we start with a query vector, and this is a little bit hard to understand. So the query vector is used to answer a question, but this question can be whatever, right? So the model trained when it learned this, but for as an example, I said, okay, so our query will answer the question, what comes before me? So let's say we are a GPU. What comes before GPU? The word overclocked. Okay, so that would be the answer. So the query vector is calculated by the embedding, and a weight matrix that is multiplied by the embedding vector, resulting in the query vector. Now we can build an attention pattern with the key vector, and the key vector is basically the answer to this query vector. So it will point in the same direction when it matches. And then the dot product is calculated between those. We see it in the matrix. And the more it matches, which people say, the more it attends to it, the bigger is the value, right? So we have, let's say for GPU, what comes before me? It was water cooled or overclocked. Yeah, overclocked, this one. That's a big one, right? It tends to this and it has a bigger value. So that's the solution of this problem. And for overclocked, it's water cooled and so on. So that's just for simplification. In reality, it's very complex to know what kind of queries are questioned by this, because there are many different attention heads, and the model finds its niche there, right? So another thing that's interesting for this matrix, the size of this matrix is equal to the square of the context size, which means if you add up the context size of the model, you need much more VRAM and so on. It takes a lot longer to compute this. So the context size is a thing that goes quadratically, basically. And if you have CUDA out of memory errors, you could start reducing the context size if that's the thing you want to do, right? Otherwise, you go down with the global batch size. Okay.
Where do the minus infinity values come from? Because I can understand that it's useful because it's as far away from matching as possible.
Okay, so these minus infinity values come from that we don't want to see future words that shouldn't influence the resulting values. So we set them to minus infinity because after applying softmax, they will turn into zeros. So they are zeroed out.
Okay, so that the current word is not influenced by future words.
Yes, exactly.
Point.
So we want to prevent later tokens to influence the earlier tokens. And because we use softmax normalization, the minus infinity is useful in this case. Instead of zeros, this wouldn't work, right? Okay, after applying softmax, it turns to zeros, as we see here. And we use the value vector, which is also calculated by being multiplied by a value matrix. The value vector is the vector we use to add to our embeddings to move it into the right location, right? If we look at what I talked before that, so the value vector is the one that we add to our, let's say, vanilla set embedding, and this will move it to the location to have the information with the right context. This is what computed here. And it will be, it will use the attention pattern to be computed. So the values are getting added to the original embedding and they produce a sequence of changes, and more refined embeddings are the result to this. Okay, let's look at this matrices just to info. So they have a width that is equal to the dimension of the embeddings. And for the value matrix, we have a trick. We don't have 12,288 times 12,288. We have two matrices. One is for downcasting the space and one is for upcasting the space. This is done to have a little bit less parameter count. Because if we look at how this whole thing looks like in a multi-head attention scenario. So this is a picture of GPT-3, and it has 96 attention heads in addition to attention blocks, and it has 96 distinct key and query matrices and 96 distinct attention patterns. And each head has its own distinct value matrices producing 96 sequences of vectors. And they are all added up in the end together using the attention patterns as weights. And for each token and position, every one of these heads proposes a change to the embeddings we talked about. We sum together all the proposed changes and add them to the embedding. So this is basically how it looks like in a real multi-head attention GPT model.
Why 96? Why not 98?
They chose it. I think we can see this when we look at scaling laws, why they use those numbers.
It's a practical value.
Probably
it could be different.
Yeah, it could be different. It has probably something to do with the HPC system they had, the amount of data, and so compute and the amount of data. And this probably was the sweet spot. But it's interesting to understand that each of those heads sees all tokens at training, and those distinct Q, K, and value matrices, each head has its own linear transformations, and they find their niche because they are randomly initialized, and during training they each have their own contribution in order to optimize the prediction. Okay, but it's hard to understand why this is the case, and that's why it's not easy to teach this in a human understandable way. Okay, let's go into scaling of LLMs, which is the key of the success, I guess, for those emerging capabilities too. And the scaling laws are used to predict either the size of the models, whatever you want to use. So more data, more parameters generally leads to better performance. And the idea is to predict model performance based entirely off the data and parameters in the scaling laws. So the question that can be answered by the scaling laws is how well will we perform when we add compute and data to our model? And at least currently, I'm not sure if this is not outdated yet, but there are no signs of plateauing. So adding data and compute is still a good recipe. But there are rumors that GPT 4.5 is not that good. So maybe we are at the end of the scaling laws theory. But for us, they are important because maybe next year we have 2,000 GPUs, and the question would be what kind of model would we want to train on those, which is the ideal model to train for. And as compute is a constant figure, we can only adapt the number of tokens and parameters, right? So I didn't calculate it yet, but maybe it ends up with 96 heads. But you also have to find a good sweet spot for the amount of training data you want to use.
You wrote there 20 tokens per parameter. That means if we have all the model parameters, we can multiply that by 20, and this is then the optimal number of
computational. It would be optimal computationally, but maybe you just care about model performance, then you could use more. This is an efficiency thing.
But you mean with the number of tokens, like all input tokens in the whole data set? If I have a certain number, like 1 billion parameters, 20 billion tokens in the whole training.
Yeah, exactly. This is meant for pre-training, though.
Okay.
It's just the first training. Mm-hmm. Okay, so now look at how this is done in reality. So one thing that makes scaling laws a little bit disappointing for researchers is that the only thing that matters in the long run is the leveraging of computation, which is a tough task, right? Parallelization things to code their low level on HPC systems, not that easy, but this is unfortunately what makes those models a lot better. So if you have a new idea, but it will break the efficiency of the training, your model will probably not be the world's best, but only maybe for a niche or for scenarios with very little data. But for us, it's a good thing, right? More compute, better models, better applications. So let's look at the training of Llama 405B, which is quite a big model. This one was trained on 15 trillion tokens and has a parameter count of 405 billion. So it used a lot of flops. I think it used 16K H100s. So 16,000 H100s is a lot more than we currently have, unfortunately, and with an average of 400 T-flops. And if we look at how long it trained at the time of the training, it results in 26 million GPU hours. That's a lot. And if we calculate the costs for this, it would be, let's say, $2 per GPU hour. So if you rent a GPU at the cloud provider, you probably pay $2 or a little bit more. So 2 times 26 million. And then I guess an AI expert should at least get 500,000, right? And of course, HPC admins too. And if we all calculate the salary, let's say Californian salaries, you end up with a total cost of just training and developing this model of $75 million. So that's a little bit of the context. And now, what do we get next? So people suspect the next model will be 10x of what we have here. So you can think about how much this would be. Now let's look into training of LLMs, which is probably something some of you are interested in. Who wants to train an LLM or who already has trained? Okay. Processors. Yeah. So I guess some more want to train something. So there are different types of training. We just talked about pre-training. So the Llama model was pre-training. The scaling laws, they care about pre-training. But there are also ways of fine-tuning a model, which is using a foundation model, which already has been pre-trained and further fine-tuning it. So for fine-tuning, we generally have full fine-tuning, which on instruction data set, but you could also do an extended pre-training. A full fine-tune needs the whole model, of course, so it's a little bit challenging. There are also ways to do it with adapters like LoRa, which are less computational hard to train. And what's upcoming also is a preference optimization, like reinforcement learning with human feedback, which was the first one used in ChatGPT. But now there are also algorithms like DPO, direct preference optimization, or GRPO, which we see now in the DeepSeek models. So let's go into pre-training one more time. So pre-training is the idea of using all available data. So download everything from the internet, extract it from HTML, clean the data from undesired material, deduplicate the data, filtering the data. You don't want to have some weird stuff inside, right? And have a nice data mix. You need a quality ranking to mix the data correctly. So Wikipedia is usually a good source, and media or some social media stuff is usually not that good. And then you have to pack it into the right format. Mostly you see Parquet files, but also for smaller ones, you see JSON-L files for pre-training data set. And yeah, right now the best models are trained with 15 trillion tokens. There are open data sets also like Red Pajama or FineWeb-Edo. I looked into Red Pajama and they really have the whole internet. I saw websites there. I thought, okay, so that's almost everything. They write really niche German websites. Everything was in this pre-training data set. So be careful what you put online. You will probably get trained on today. So, but that's also
the point, right?
And Hugging Face available?
It's on Hugging Face. I used it because I had a list of URLs that I wanted to just train on. And this was a good way to have it already pre-processed, right?
Yeah.
So I didn't have to do this whole web scraping stuff because apparently the whole internet is inside. Okay, but there's also FineWeb-Edo, which is a little bit nicer. It has, it's furthermore pre-processed with an additional LLM use. It's a lot cleaner. So, yeah.
A question for pre-training. I know that I think Microsoft had the Orca approach that they used. I think GPT to create pairs of prompt and answer. They use that for pre-training.
Oh,
I guess that's
yeah. So yeah, if we could choose, right? If we could choose using high-quality conversations with 15 trillion tokens, we would do this. Right? This is just the best we have. But if you could process all of this, the whole pre-trained data set into more high quality structures or condensed information, this would be ideal. But it would be expensive.
It has been done like to some degree. Large language models to extract high quality data and to train a small language model with that, which performs almost as well as the large language model.
But then you just use a lot of compute beforehand, which is almost the same. And FineWeb-Edo is one example for this, right? So it feels a little bit like you use a lot of compute to pre-process all of this, which results in better model, but again, it's compute somehow. So another example is Llama 2. This was trained on 2 trillion tokens. They usually chunk those texts into fixed sizes for efficiency. So 2 2048 or 4096, and the context window extension is done afterwards in most cases. And these are...
Does that mean that knowledge I can extract from it is limited to this kind of window? So if there's a long article with a long chain of reasoning, chops it into pieces, and this is detrimental?
Yeah, not only chops it, it also randomly throws it. So the model sees just random text chunks by training. Yeah, that's correct. But later on, and with additional trainings, the context understanding is extended. And it seems like you don't need that much data to do this after this. Because if we do this if we use a much higher context window, and I told you before, the attention pattern matrix will be quadratically upscaled, right? It would take a lot more compute hours to train those models. And if you see here, a 7B model takes 184,320 compute hours. So if you want to train this at our cluster, it's already almost impossible to get that many compute hours right now at one run, you see? So pre-training might not be the most interesting thing for you guys. I would rather do instruction tuning. So instruction tuning is a way to make the model follow conversations. And in my opinion, this is the most important thing that got invented for those GPT models, because it enhanced usability, right? So when I started, I used GPT-2. It was only a completion model, and you always had to think about the text that it has to complete in order to get the answer you want. And just this small process of rethinking was very hard, and using instruction tuning, it suddenly made it follow your direct requests. Like you talk to it like a human almost. And this small change in the user friendliness, like in usability, made this whole technology become so famous, in my opinion. It was usability, and usability is more important than features all the time for every software. But in this case, it really made it the most popular software like this, you know? So most of those instruction data sets are created synthetically and filtered afterwards. You have to look at it like this. You have a text of something, and now you want to have a conversation about this text, or you have information about a certain task, and you can generate a conversation about this. And then you have a data sample, which is used for fine-tuning the model. Right? It goes like you have an input and you have an output. Okay, let's go into evaluation of LLMs a little bit. The evaluation of LLMs, there's a metric called perplexity, which is the validation loss, and the average per token loss is exponentiated, and the perplexity is between 1 and the total vocab size. And the value of perplexity is the number of tokens the model is hesitating between for the next predictions. So the lower the number of it is hesitating between, the more accurate the model predicts the next word. So perplexity is used for next word prediction, so for evaluating pre-trainings most of the time. So we also have MMLU benchmarks like multitask language understanding, where we examine the performance of instruction-tuned models, right? You get a question like, what is true for a type 1A supernova? And then you have multiple choice tests and should predict the right answer. So this is used for models that are already instruction following, right? So because a completion model would start writing the next question, right? It would complete the text. But an instruction following model, it would answer this, hopefully correct. Now, let's get to something that is very important for training models on our HPC systems. We need parallelism, because those models can easily be bigger while training than the VRAM of one single GPU. And that's why we look into this. First, we have a parallelization technique, which is the most simple one. So in this case, we see a model fits into each device, and we split up the data into smaller chunks and give each model on the device one of those chunks. Okay, that's data parallelism. We just get the batch size up, so we have more average updates. Looks like this. A batch gets split up between the models. The weight updates are combined with all reduce operations. But there are shortcomings of this technique, that we cannot scale infinitely, like 3,000 GPUs, because the batch size has to be big enough for one example. If we split this up too tiny, right, then it's not big enough for one example. And what if the model doesn't fit into a single device? Then we have a problem, right, with this technique. That's why we also need model level parallelism, and they are essentially tensor parallelism, which splits the layers horizontally, and pipeline parallelism, which splits the layers vertically. So tensor parallelism is something very complex, which currently not all frameworks support. So if you use just Torch, it likely doesn't have tensor parallelism in your training. But pipeline parallelism is more widespread because it's easier to handle the communication between that. The only problem here you can face with bubbles if you set the value not correctly, because those batches come in, and so that's the forward pass, right? It gets filled up in the forward pass and then goes in the other direction with the backward pass, and then you have those updates.
Have you filled the bubble with a different training?
Maybe. There are many techniques, like there are many papers that care about minimizing those bubbles, but I don't know if any of this is now really widespread used. So the current state of the tech of Megatron is this. We can, of course, optimize the TP and PP. We want to probably use TP for on your node. So the communication of tensor parallelism is very intensive. So you want to do this on a node level and not across nodes. And here are some charts on how to do this. We're usually the same number of GPUs for TP and PP on node level. So if you look at all those techniques, we have this 3D parallelism thing. We have data parallel on one axis. Zero data parallel just means that also the optimizer states are charted across those GPUs. And pipeline parallel, we saw this. Okay, here's the zero parallelism. It is essentially data parallelism, but the gradients and optimizer states are also split up, and each slice is on a GPU. So when do you use this? If you use deep speed, for example, or FSDP, they should support those different zero levels of splitting up those parameters. Another thing that is essentially a parallelization technique are MOE models. So if naive people sometimes think those MOE models are real experts in something, but in reality, it's just to optimize the use of compute efficiency for large-scale LLM trainings and optimizing the processing power. So what those experts really learned can be totally out of control, right? You could have an expert that does perfect German, but also Chinese, whatever. Yeah, where this is located in the model will be entirely, you won't be sure about this. So it's basically a trick about optimizing processing power. But there are also some cons, and that is tougher to fine-tune an MOE model. It's a little bit more hard. And you need higher VRAM usage compared to dense models.
What does it mean activating only relevant model parts?
They say this. So at inference, it uses only a part of all parameters. So the token prediction is faster, but you still need the whole VRAM to load the model. So we see this with DeepSeek 600B. It runs on our AMD node, for example, because it has a lot of VRAM, but at inference level, only parts of those parameters are actually used. Makes it a little bit faster, but still 33 tokens per second is not super fast. Yeah. Let's go into LLMs on HPC. So let's go into some real world examples. You have a single GPU and your model fits onto this single GPU. You can just use it in a normal way, train it. Very easy code, no crazy communication, not a lot of packages that you need. But if it doesn't fit into a single GPU, you can try offloading onto CPU. You can try the zero data parallelism, which has those offloaders, and optionally on NVMe, but then it gets really slow. The training gets slower, right? If you offload on CPU, it gets slower. Or you use adapter training to handle this.
With offloading on CPU, you mean offloading to the host memory?
Yeah.
It's like
exactly. RAM.
Faraway cache or whatever.
Yeah. Okay, let's go single node. So the model fits into a single GPU is also always the best case if you have to code it yourself. Then you can just use data parallelism, distributed data parallelism. If it doesn't fit into a single GPU, then you have to go into this model charting things, right? Usually DeepSpeed or FSDP can handle this for you. This will be fine. So TP is something we only see at Megatron or Megatron forks right now. this is a tough software to use. It's expert level, let's say it this way. I will later talk about those frameworks, but this can be also used to optimize this, and this might be the fastest way to train your model. So if your model fits into a single node, I would first try zero offloading. If you go up, for example, the context size, so if you get an out-of-memory error, I would say 0-3 strategy for this one. So it might be able to train it on one node. If this still doesn't work, you probably have to add more nodes, which becomes quickly a little bit more challenging from a configuration perspective. So if you look at the frameworks you could use, this is also something I think that's very important. Many people want to train models, but they don't know yet which framework they want, right? Maybe they start on their workstation and they have Onslaught, for example. They started training on one GPU, but Onslaught is also only made for one GPU, right? So if they move to our HPC system and they want to scale it, I think Onslaught is out of the question right away. So they have to move up. And then there are different frameworks for different things. I think if you do a large-scale pre-training, you probably should use Megatron LM because it's the fastest training framework for pre-training. And if you want to train for, let's say, 180,000 GPU hours and you're 30% faster, that's a lot of GPU hours. But for fine-tunings, I would recommend usability first because you have good, fast results. Maybe your fine-tuning only needs 2 days. So it doesn't matter if it needs like 48 hours or 40 hours. We can discuss this. But I mean, the hours you have to put into something like Megatron will be a lot more than what you save for fine-tunings. So you have to find out which kind of framework is best for your use case. And that's sometimes challenging because if you start looking into something and you later find out you don't like this or you don't proceed that fast, there's a lot of ways you can waste time. LitGPT is something very interesting because it's minimalistic. You can easily change code for your research, and it's even developed for research purposes. So this is quite straightforward. And for research, I think is a very good way to go. There's also Axolotl, which is an open source project. I like this the most because it has very stable loss curves with using leap speed. You can easily configure a lot of fine-tuning styles through the configuration. So you can freeze layers, you could add other settings you want to try out. So those combinations can be something new, right? And the resulting models never disappointed me for Axolotl. With LitGPT and FSDP, I had some unstable loss curves, for example, using some precision modes that I didn't like. So there are also inference frameworks because sometimes you want to generate data, which is very important, I think. So generating data, high quality data with the right data augmentation in the process is something that can work to improve models and even beat high scores. So for inference frameworks, I would advise to use VLLM if you do it at scale. So if you really want to generate a lot of data, use VLLM. It can run on our clusters too. You could also use SGLang, which is another library on top of VLLM, but essentially the same. There's also XLLama, which is optimized for running quantized models, or TGI. It's a text generation inference. For VLLM, I have to say it already does the batching. So you could use multiple workers to consume the endpoint and your node will be stacked. So 100% usage. That's a nice thing. What you shouldn't use, in my opinion, is OLAMA or transformers, for example, because that's not very optimized and very slow. And OLAMA is designed, I think, for workstations, but some people tried it also out on our systems. And it has one advantage that you can use an uneven number of GPUs if you have to. Other than that, there's also text generation web UI. I like this for testing models. If I have a quick training run and just want to test it, that's for quick evaluation if your model is total trash or works, right? So this is basically it. So now I'm already at the end of my slides, so we can have some questions or discussions.
There was some discussion in the chat about quality of training data, so that the internet is running out of data to train our models. Yeah, is that true?
Yeah, so I mean, what we saw and what I did in my work also, we used internet, like publicly available data that all those models have seen, but found out a smart way to prompt this into conversations, but also by combining different data sources, which led to new instruction tuning data, which improved our model a lot, right? Even over GPT-4 level. And all of those models saw the internet data before. So I guess a smart combination of data sources and a good synthetic data generation pipeline can really help your model still, although it saw it in the pre-training. So there are ways to get more out of this data, probably.
Formula or possible calculation to know how many epochs need to have a good model in per-training station.
How many epochs?
How much epochs needs it to model
to become good? So in general, so for the pre-training, it's just one epoch, one huge epoch. And you can, of course, can guess how good your model becomes in such a large scale, right? If you look at the scaling laws, that's the way we can think where you will end up in performance. But for your fine-tuning for smaller data sets that you don't know how they will perform, maybe they are not that good. Maybe the model doesn't learn something because they're too easy. So if you, for example, for those radiologist reports or medical reports, they're usually very, very short and very easy to understand. And then the loss will go down like whoop, almost to zero. But it's still not that great because the data set is not really good. That's one scenario. Or it cannot learn anything from it. This happened to me while training on academic reviews. So basically, they didn't make a lot of sense for the model. And yeah, then you see a loss curve, like if it's totally random. That's the case. Yeah.
Know something about vision transformers, like such properties would also apply to like vision transformers when you're training in like a multimodal pattern, like with pictures and.
I'm not 100% sure how those multi-model models work, but they are like, let's say we have a Llama 70B, and then you have 20B vision part added, and then you have those projection layers. So probably they are trained individually and then aligned through those projection layers. But you can also train vision models with the same frameworks partly. And you can say which type of layers you want to train. Let's say you only want to train on the projection layers and you have everything else frozen. It's also possible.
I guess you have fine-tuned or trained a lot of LLMs already, or at least for different use cases. Here, what are your lessons learned here when someone wants to start training LLMs? So what are probably the most important things to be careful about?
I think that the easiest way to do something wrong is not using the right chat template, for example. Don't use the right chat template. Also, it depends on what you want to achieve. If you want to train your model only on your task, okay, then just use your data set. But otherwise, you need a diverse data set to not make you a little bit weird, because then it faces those catastrophic forgetting things or others. So you should find out which data correlates well with your task. You could add this to your training. What else? Out of memory errors are super annoying. So always start with microbatch size 1. See if it works. Look up the VRAM utilization and then go up with microbatches. Context size is a thing. Use only as much context size as you need for your task, not too much. You can still later extend this, maybe if you care about this, but it will make your training slower. Then you have to calculate in terms of token per iteration to have a feeling about this batch size too, right? So if you have a 16K context window, you have a lot more tokens the model will see during one iteration, and your total batch size might vary a lot. So this is something you have to keep in mind. What else? I stick with deep speed and 0.3, something like this. I don't like FSDP, but that's more like a feeling. I have no real evidence for this. There's a lot of us, like what I saw is in those Discord groups, there are a lot of people who have their recipe thing, right? They try just everything out. And I guess in those communities, you can also learn a lot.
Discord, you see.
Yeah, in Discord, so these frameworks have their own Discord servers, and you see what type of problems did they have before. But also you meet people who work on the same stuff and face the same problems. I'm not sure what else. Yeah.
No token storage.
Yeah, if you have many small files, then you should do this. And also those frameworks have like hidden spots where they still write on NFS storage, like caches, something like this. Oftentimes you overlook this because many of those frameworks are not entirely designed with Slurm in mind, right? They're sometimes for other setups, for a lot of them for Kubernetes. Some are even just used on single servers. So that's something you have to look at.
There's a question there, yeah.
And you briefly talked about these expert models. Like, can you comment on like the regional distillation? Like, how does that play in? Is it
okay? Yeah, I'm not sure if this is related to the MOE model, but the distillation, I saw it in the context, let's say, with DeepSeek, where you have those reasoning traces that are extracted from the bigger model and then used for a straightforward fine-tuning on a smaller model. So this is something that works. So the bigger model might have more from a reinforcement learning style, like the GRPO style of DeepSeek. Let's say they use GRPO for the bigger model, and it benefited a lot from this. And then to make it more efficient, they just generated outputs from the bigger model and used them to train on a smaller model and reached almost the same performance. I think that's the idea behind this. Yeah, and that's what many people do.
Have you tested this already?
We did this a little bit differently. We created our own thinking recipes and dynamically added them to our data because in my domain, you cannot really reason to it. The GRPO works well if you have one single answer, like for a math question, and then it goes through it and gets rewarded if the way to it was correct.
So you showed examples of quite large models, so already models. What's the size of typical model which is great for so like
Okay, so I think most models used currently are 7 billion parameters or 8 billion parameters, what I see a lot of the times, and they are probably 13 gigabytes or 14 gigabytes in size, roughly this size, because they
fit on one GPU basically.
So this depends on the training style. If you do a full fine tune, you might not be able to have it on one GPU. But if you do an adapter training or you have a super large GPU like our MI300X, then this will fit.
What would you say is the limit in parameter size for pre-training on the HPC?
So we had a 7B model pre-trained. Gerhard, can we do this again? we have this Lamline model 7B pre-trained on 3 trillion tokens in German on our HPC system.
How long did that take?
Do we know the GPU hours they use?
weeks, 10 weeks or something like.
Yeah, if we see, let's see. I had some numbers.
I will check the consumption.
Yeah, there we have some numbers for 7B, for example, 7B, but this were older GPUs, okay, not that fast. 2 trillion tokens, almost the same amount, and they took 180,000 GPU hours. So this is something, if you don't ask way ahead of time, you might not get the allocation of this. I'm not sure if we are the right side for this. Maybe also bigger.
I would say 100 to 150,000 GPU hours in an age.
Yeah,
something like that.
but that's not something we can regularly do, right? That's
20 GPUs for 1 year.
Yeah.
Or 240 GPUs. What is the price tag for 240 GPUs? Something like 5 million euros. 7 million. So these are really expensive trends. You shouldn't do them on do 10 different master pieces and evaluate different strategies.
And what I also can say about this, it's not trivial to scale those trainings across those nodes reliably. I mean, you have to train it for 150,000 hours. You have to resume from checkpoints, and everything has to go smooth, right? It has to be optimized. You need full load on each node. This is something that takes a while to learn this and do this. especially if you use a framework like Megatron. Even what we used, LitGPT, we had also some difficulties, right?
I have a question. Is there a difference? So when I want to do fine tuning for different things, for example, like interpretation of some data or another fine tuning, like writing mathematical formulations, like are there different things that I need to look out for generally? Like, is there different in the method of the fine tuning? If I fine tune it for different purposes, or is the method always?
So generally it's called SFT, right? So you have a structure of your data that will be used by your framework, and you get an input and an output. So the training style is the same, but there are some settings you can set. For example, don't train on inputs. I have this because my input oftentimes begins the same. I don't want to have the model learning always the same start. Like we'll always say this sentence then. So you can mess around with this. You can use sample packing if you want. So you can add more of this to increase basically your batch size instead of just padding. But so the training is exactly the same.
Okay. So like, what is basically what kind of data do I need, or like what's the minimum size of data?
That's a good question.
Yeah. Fine tuning.
That's a good question. I'm not sure where the hard thing is, but if you come to me and you say you have 12,000 samples, I would say, okay, let's go. If you come to me and say you have 300 samples, I would say, no. It doesn't make sense because you have this warm-up phase, the model gets a little bit loosened to get the training, and it just gets weird if you just have 300 samples.
Mm-hmm. Okay.
But then you can still use adapters, for example. This would be a safer way to do this because you don't mess with all weights. You just have those added layers. They are good for like restructuring tasks, not for getting new knowledge into the model.
Mm-hmm.
This is more difficult. So one challenge is probably to get really new knowledge into the model without a lot of data. It's hard. Humans can do this, right? I touch my hot plate or whatever in the kitchen and I will know, okay, it's not good. But they have to see it a lot of times, I guess.